Okay, so in this part of the lecture, we're going to deal with partial pressure. So partial pressure, so everything up until this point has been dealing with a single gas, okay, or treating a gas of a system as a whole thing, okay. In some cases, we have mixtures of gases, and we want to be able to isolate independent parts of a mixture of gases. So for example, okay, we breathe in nitrogen and oxygen, smidge of carbon dioxide, and so the pressures related to each one of those gases gives us a partial pressure. So another example that I'll often refer to is your tires. Okay, when you put air in your tire, you have a contained system that has nitrogen, oxygen, little carbon dioxide in it, and so the pressure in your tire is your total pressure. When you put the pressure gauge on your tire, you're measuring the total pressure. Okay, it doesn't tell you the pressure of nitrogen in your tire, but if we wanted to calculate the pressure of nitrogen in the system, that would be a partial pressure of nitrogen within that system. Okay, so each component of the mixture, so if we have 7 or 8 gases, the sum of each one of the partial pressures of the system adds up to the total pressure of the system. Okay, so this is what you see here. Okay, is you have the individual gas, okay, say a little bit of oxygen, a little bit of nitrogen, and the total gases combined equal the total pressure of the system. Okay, so unless you fill your tire with nitrogen, which I hear we can do, they do now, we have to separate them out in order to find the individual pressures. Okay, so what you're going to see here are essentially some, again, transitive equations where we're looking at the ideal gas law in a different way. Okay, so the top equation here is the same ideal gas law that we just looked at, PV equals nRT. The only difference here is the T means total, okay? So the total pressure times the volume equals the total moles times RT, okay? So this is the total, if we're only talking about a single gas, so before we didn't designate it as total, right? Because if we're only talking about a gas, like, what is the relationship if I increase the volume, and pressure, or the volume of some gas of hydrogen, at some temperature and pressure, if you're just dealing with a single gas, there's no need to designate it as total. It's the only one, so we don't need to say its total value. So here, we're just redesignating our PV equals nRT to say that the total value and the total moles are gonna be in the ideal gas law. Or we could look at the individual partial pressure. Okay, the partial pressure of one part of the gas is equal to the volume. Again, the volume's not going to change. So like your tire, for example, your tire doesn't change volume. Everything in there, all the gases inside your tire are the same volume, right? So the moles of that individual gas, R and T, again, all the gases within the system are the same temperature. So we're not changing things like various temperatures, because again, you're assuming your system is uniform, okay, that everything is mixed uniformly. So my tire, everything in there is the same temperature, everything's in there the same volume, R is just a gas constant. So the only variables really are the pressure and the number of moles of stuff, okay? So the summations should be relatively straightforward, okay? The sum of all the partial pressures adds up to the total pressure. The sum of all the moles in the system equals the total moles in the system, okay? If I have oxygen and nitrogen and carbon dioxide in my system, then all of those moles added up are the total moles in my tire. there's nothing else in the tire other than those three gases. So when those three gases are summed up, that's everything that's in there, okay? All right. So this brings us to one way to differentiate some of our, or present some of the information here is a percentage. So here it's called a mole fraction. So it's just a percentage value of the gas in the system. So if we know that oxygen in the air is roughly 21%, then, and most of the rest of it is nitrogen with, like, you know, some small percentage is carbon dioxide and some other stuff, then we can represent the percentages as a mole fraction. So it's just the individual moles over the total moles, okay? And obviously the mole fractions add up to 100%, right? So if you have 10% and 90%, they should add up to 100%, right? If those are the only gases you have in your system, there's two gases, we have nitrogen and oxygen. So the sum of all the nitrogen and oxygen percentages should add 100%. There's nothing else in the system that adds to our percentage, okay? And so here we have another equation here that has the partial pressure. So this is, like I said, there's a bunch of different ways that you can solve some of these partial pressure problems. If I wanted to know the partial pressure, if I know the total pressure and the mole fraction, so the total pressure times the mole fraction tells me the partial pressure, okay? So this is like, if I know what percentage I want to, you know, of my total, okay, tells me like how much I'm going to tip, right? So if you have your total bill times the percentage, that's going to be your, you know, your tip, right? So if we're, you know, if our bill is $30 and we're tipping 15%, you know, or 20%, then that tells you what your tip is, right? So it's the same kind of thing. All right, we want to know what is the part, right, that contributes to the total. All right, so finding the partial pressure can be used with this equation. Sometimes we're given the total pressure, sometimes we're not. If we're not given the total pressure, then you can come back here and you can always use the ideal gas law. Using the ideal gas law is always a good way to go. You don't have to use other equations. You can do this. Again, if you're trying to get the answer, it really doesn't matter. Most of these problems, you're not going to get away with, like, it doesn't make it faster or something like that to solve it one way or another. I mean, most of the time we should be focused on getting the right answer, not trying to get it done as fast as possible, okay? So there's a couple different ways that we can solve for partial pressure. Okay, so the question here is, find the mole fraction of neon in a mixture with a total pressure of 3.9 atm, given the total volume, temperature, and 0.7 moles of xenon. Okay, so we have xenon and neon in a mixture. Okay, so this is what we're given. Okay, we have a total pressure, the volume of the system, the temperature of the system. Again, these are going to be constants for everything. And we have the moles of xenon. All right. So this goes through a couple of steps. This is why when we get around to doing the practice problems, we'll probably spend a bunch of time working on these kinds of problems, because they take up a little bit of time to sometimes solve. Because again, these are difficult because they're not quite intuitive of how do I solve this? What do I need in order to go about doing this, especially when there's more than one way to solve these, okay? So this particular approach looks at, given the moles of xenon, okay, the temperature, the volume, and R, they could calculate the partial pressure of xenon, okay? If we have the total pressure and we have the partial pressure of xenon, well, then the remaining gas must be the neon in there. And so we can also then calculate out the mole fraction, okay? All right, so here's the first one, Okay, so this is using the ideal gas law. So this is a rearrangement of the ideal gas law to find the partial pressure of xenon. We're told the moles of xenon, so we want to know what is the partial pressure of xenon. Again, there's only two gases in there. Okay, you have the total. Okay, the two gases equal the total. So if you know this one, right, and the total, then you just have to subtract, right, in order to find what's left over, right? So that's essentially what they're doing here. Okay, so here's the total minus the xenon, which they just found over here. The rest must be the neon. Okay, so it's only those two components, right? The partial pressure of the neon plus the xenon equal the total pressure. So just subtracting out the xenon tells us the partial pressure of the neon. Okay, last is a rearrangement of the other equation, okay, where we have the total and the mole fraction. Here, the partial pressure of neon over the total pressure is the mole fraction of the neon. Okay, so this one's a little complicated. Okay, I'm not gonna lie, this one's a little complicated. All right, it's not the most complicated problem. All right, we will, when we do the practice problems, there is one that is harder. Okay, that deals with we have two sets of gases and we open a valve, and then the gases mix, and then now what are the new partial pressures of the individual gases in their new environment. Okay, so but these can get difficult quickly. Okay. This looks like the similar problem. All right. All right. So this one, okay, so this leads into gas collection over water. Now, when we do labs, this is generally one way where I have a lab that we could do for gases, entirely up to to you guys, to how much more work we want to do. Again, I think if we do one more lab, this, we shouldn't really need to do too much of this. But one way to collect gases is to do it over water. Okay, so if we have a gas reaction, so one of the labs we used to do was when you take a metal and you mix it with hydrochloric acid, it produces hydrogen gas. And so what it would do is it would bubble the hydrogen gas up, and we would collect the gas in a volumetric cylinder. And so then we could measure how much gas there was, because it would displace the water. It would push the water down as the gas collected, because we took the volumetric cylinders and tipped them upside down and put them in water. And so they were full of water all the way to the brim, and we put a little tube up underneath into the volumetric cylinder. And so then the bubbles would come up into the volumetric cylinder, and then it would displace the water and push the water down. And so we could measure the volume of gas collected. Now, the reason why we have to talk about vapor pressure here is because anytime that we have water, there's some amount, a little bit of water that escapes into the vapor phase. Okay. And so it creates a mixture, a gas mixture. So in our cylinder, when I was collecting hydrogen gas, it's not just hydrogen gas in there. There's also a little bit of water vapor that's mixed in there as well, that we just have to subtract out. Okay. So water vapor depends on the temperature of the water, obviously, but any type of vapor pressure deals with temperature. So generally we would say things that are more volatile, okay, have a very high vapor pressure at low temperature. So when you take acetone, right, if we spill some acetone on the counter and it just evaporates, right? Or some gasoline, right? You spill some gasoline when you're filling your car, and the puddle just kind of goes away. It evaporizes really quick because it has a high vapor pressure. So that means that there's atmospheric pressure pushing down, and the question is, well, at what temperature does the vapors pressure pushing up overcome the atmospheric pressure pushing down, right? So it's an equal and opposite forces thing from physics, okay? You have the atmospheric pressure that's pushing down. Water, as we heat it up, its pressure of the gas that it has to overcome in order to escape into the gas phase starts going up until it reaches 100 degrees Celsius, at which point the atmospheric pressure pushing down is equal to the vapor pressure pushing up, and then it allows everything to escape into the gas phase, right? So for things that are volatile, like gasoline or acetone, they escape into the gas phase at a much lower temperature. We don't have to heat them up very hot for them to have high enough vapor pressure that they overcome the atmospheric pressure pushing down on them, okay? So when we have a mixture, and so this is kind of reminiscent of the experiment that we used to do. It wasn't, in this case, potassium chlorate or, and the manganese, but it was more of a, like this, where we had a metal with HCl, and the reaction created a, hydrogen gas, and then it went around and it bubbled up through here, and then it displaced the water. So in here we have hydrogen gas and we have water vapor. And so we just have to subtract out the water vapor. But here's the thing. We know everything about water. We know everything about water. So that means any temperature, you can know what the vapor pressure of water is at any temperature. So that means it's not really an unknown value. So when we have pretty much any temperature, we can, and like I said, there's a CRC handbook where somebody probably measured it in single degree increases, like 66 degrees and 67 degrees and 68 degrees. And so we know what the vapor pressure of water is at pretty much every single temperature, right? And so we just need to subtract it out, right? We have the total pressure, right? That's the atmospheric pressure. If we know the temperature of the room, then we know the vapor pressure of the water, and we can just subtract it out of the total, and that leaves us with the vapor pressure of the hydrogen gas that we collected. Okay, so here at this experiment, it's at 25 degrees C, so the vapor pressure of water is 23 torr, right? And so the total pressure, okay, again, this is something that would be given because this is like something we measure on like a barometer for the atmospheric pressure. What is the atmospheric pressure? And then we just subtract out the water. And so the remaining part is, in this case, the oxygen, but in the lab experiment, it was the hydrogen because we were collecting hydrogen. And so what is the vapor or the partial pressure of the hydrogen or oxygen is just subtracting out the water part, okay, after we collect it. All right. And so that's really the only trick for the gas collection over water is just subtracting out the water. Is when we're given a gas collection over water, we just have to subtract out the water in order to get the partial pressure of our gas. All right. So the last thing deals with gases and chemical reaction. Okay. So let's look at this flow chart. So this looks very similar to the flow chart that I was using, okay? Again, this is from the book, so it looks a little bit different than the one I was using, okay? Right, so here, they kind of put things in just a slightly different order, but it's not too difficult to see where they're going with this, okay? Here's the volume of some reactant A, okay? Molarity, right, got us to the mole. So I put the volume over here in the middle, right? Here's the mass and the molecular weight. So in my diagrams, I put the mass up top, right? This was from our second chapter, right? The number of units. So Avogadro's number told us the number of molecules there were, right? So if we had the number of molecules, right? And then, so in this chapter, it's really just adding this part, okay? What is the it's the volume, really. It's the volume is really what we're interested in here, is the volume of gas. So here we have volume of liquid, mass of the substance, and the volume of the gas. So it can use PV equals nRT, but there's actually an easier way of doing this, and that involves what's called molar volume. Okay, at STP, okay, if we calculate the volume of gas at STP, right, the volume of 1 mole of gas at STP, okay, if we plug that into the PV equals nRT, 1 atm, what is the volume? 1 mole of gas, R is a constant, 273 Kelvin. Pressure, standard temperature and pressure, and 1 mole. The volume is always 22.4 liters. So this doesn't matter if this is, sorry, wrong button. So this doesn't matter if this is oxygen or xenon or chlorine, right? It's agnostic of what the gas is. Any gas at 1 atm, where we have 1 mole of the gas, they all have the same volume. Okay, it's kind of another one of those convergent pieces of data thing, right? We have convergent data points. Like, this has clearly got to mean something if every gas has the same volume at STP, right? If 1 mole of every gas has the same volume at STP, that must be important, okay? And so what this gives us is kind of like a molarity, right? So what is molarity? Moles per liter, right? In this case, it's telling us how many liters there are per mole. So it's kind of like an inverse molarity, right? So that's how our equation worked. That's how our equation worked before for molarity, right? So here's the equation slightly shifted now. So now we can use molar volume to calculate between volume and moles, just like we use molarity to calculate between volume and moles. Okay, so this is a given for each substance. Okay, so this allows us to do, again, 3 basic steps for most of the stoichiometry kind of problems. Okay, given the mass of A, I want to know the volume of gas. Okay, so it's 1 step. Step 2 is the balanced equation. Step 3 is the molar volume, right? I want to know the mass of some substance produced from gas. Well, the molar volume, balanced equation, molecular weight, right? If I'm trying to get to the mass, right? Molar volume, balanced equation, molecular weight. So it allows you to basically still do any of our, pretty much most of our stoichiometry problems in about 3 steps. Okay, now this only works, okay, here's the key. This only works at STP. Okay, if it's not at STP, you have to use PV equals nRT. Okay, if it's not at STP, you have to use PV equals nRT. Right? So it doesn't make it quite as nice and neat. It doesn't fall into our 1, 2, 3. Because if you have to stop here at the moles and then calculate everything to PV equals nRT, it's a little cumbersome. It changes the slight flow dynamics of doing our 3 steps if it's not at STP. Okay, so most of the problems here will probably likely be at STP. Right? So here's a type of stoichiometry problem. How many liters of oxygen at STP can be made from 100 grams of lead-4 oxide? Okay. All right. So here's our 3 steps. Molecular weight, grams to moles, balanced equation, molar volume. Okay. Molecular weight, balanced equation, molar volume. Okay, here's the molecular weight of the lead 4 oxide, the balanced equation right here. So there's 2 moles of the lead oxide for every 1 mole of oxygen, and then the molar volume. So multiply and divide, and we get the volume of gas at STP. Okay. Questions on this so far? The stoichiometry should be relatively not much different than what you're doing right now. Okay, so if you did okay or you're feeling confident with the stoichiometry for chapter 7, this is not changing anything much. Okay, it's not really changing much of anything. The only thing here is going to be the molar volume that we have to take into account instead. So it's just like a mole, you know, instead of moles per liter, it's liters per mole. So it's just like an inverse molarity. Okay, so that's really the only thing you got to change for this chapter is the inclusion of the molar volume. Okay. No, in that problem, you do not use the molecular weight for the oxygen. Sorry, my thing stops sharing. Right? Because here we're trying to get to the volume of the gas, right? So it's the mass of the lead oxide, right? There was the molecular weight for the lead oxide. We had the balanced equation and then the molar volume to get the volume of gas. So it's not measuring, it doesn't want to know the mass of the oxygen. If it wanted to know mass of oxygen, yes, you would do the molecular weight, okay? If it wanted to know the mass of the oxygen, yes, you would do the molecular weight. But in this case, it wants to know the volume. And so we don't need the molecular weight for the oxygen. Okay, we use the molar volume as that last conversion. Okay, which you see right here. Okay, so it's the molar volume because we're trying to get to volume of gas. Right? So in chapter 7, this would have been molarity, right? Because if we were trying to calculate the volume of an aqueous solution, some aqueous product, we would use the molarity in order to calculate its volume. Okay, so mass, step 1 with the molecular weight, balanced equation, molar volume to get to the temperature, or really the volume of the oxygen gas. Thoughts, questions? This is a Daisy chapter. It's a quick chapter. I'm not going to push too far tonight. I know you guys are working on your test. We don't need to push too hard. You guys can, finish doing your stuff for your test. And like I said, we still have time. We got plenty of time. We got really this chapter to finish and one more chapter to do, and then our final exam. So, we're doing okay on time. We don't really have to push ourselves too much. Okay. So